After detection, there's a small window of time within which follow-up, light-based astronomy observations can be made. In 2015, the iconic laser Interferometer Gravitational Wave Observatory, LIGO, made the first-ever tangible detection of gravitational waves. The waves were the result of two black holes colliding far away in the universe. Since then, a wealth of such signals from merging black holes, neutron stars, and even a couple of mixed mergers between the two have been spotted. Yet, despite the success of LIGO, located in 2 U.S. sites and supported by the Virgo detector, located in Italy, and Japan's Kamioka gravitational wave detector, KAGRA, astronomers have only been able to confirm one of these gravitational wave-producing events using traditional, light-based astronomy. That event was the merger of 2 neutron stars, which produced the gravitational wave signal GW170817. Now, a team of scientists from the University of Minnesota has developed software upgrades that can help alert astronomers to merger events just 30 seconds after gravitational waves are picked up on Earth. This early alert system should allow more merger events to be followed up on with light-based astronomy. With this software, we can detect the gravitational wave from neutron star collisions that are normally too faint to see unless we know exactly where to look. Andrew Toivonen, team member and a PhD student at the University of Minnesota Twin Cities School of Physics and Astronomy, said in a statement. Detecting the gravitational waves first will help locate the collision and help astronomers and astrophysicists to complete further research. What are gravitational waves? Gravitational waves are tiny ripples in the fabric of space and time, the two of which are united as a single, four-dimensional entity called spacetime. Such ripples were first predicted by Albert Einstein in his 1915 theory of gravity, general relativity. General relativity predicts that gravity arises from objects with mass that warp the very fabric of spacetime. The greater the mass, the more extreme the curve, thus explaining why stars have a greater gravitational influence than planets do. Einstein also theorized that, when objects accelerate, they cause spacetime to ripple. These ripples are only perceptible when truly massive objects accelerate, objects like neutron stars and black holes that swirl around each other in binary systems and emit gravitational waves as they do so. This continuous emission of gravitational waves, Einstein said, would carry away angular momentum and cause the ultra-dense objects to draw together and eventually merge, a collision that sends out a high-pitched scream of gravitational waves. Einstein, however, thought that even gravitational waves from objects significant enough to generate them would be too faint to ever be detected here on Earth. Fortunately, he was wrong. Still, spotting gravitational waves is still no mean feat after all. Neutron star and black hole binaries are located millions, sometimes even billions, of light years away, and gravitational waves lose energy as they travel through the cosmos. For LIGO to detect gravitational waves from these events, this massive laser interferometer consists of 2 L-shaped arms, each 2.5 miles, 4 kilometers, long. When in phase, laser light shines down each of these arms. This means that when the beams meet, the peaks and troughs of their waves line up, and the laser light is amplified, which is something called constructive interference. However, if a gravitational wave passes over one of these lasers in space is squeezed and stretched, then the laser passing over this section of space would be knocked out of phase, meaning troughs meet peaks, and vice versa, resulting in destructive interference, and thus no amplification. The changes LIGO picks up to, here, gravitational waves are 0.0001 times the width of a proton, particles that sit at the hearts of atomic nuclei. To put this in standard astronomy terms, that is equivalent to measuring the distance to the nearest star, Proxima Centauri, about 4.2 light-years away, within quantitative accuracy equal to the width of a human hair. LIGO, Virgo, and KAGRA are currently in their 4th operating run, which began on May 24, 2023, and is set to last until February 2025. Between each of the previous operating runs, scientists in the LIGO/Virgo/KAGRA collaboration have upgraded the software used to detect the shape of gravitational wave signals, track how this signal evolves, and then estimate the masses of the neutron stars or the black holes that smash together to create the signal. This software also sends an alert out to other scientists. Thanks to simulations created using data collected from observation periods 1 through 3, as well as artificially generated gravitational wave signals, the team now knows upgrades can be made to the observation software that allows alerts to go out within 30 seconds of a gravitational wave detection during observation. Such upgrades will impact observation period 4. That should help astronomers track the locations of these events in the sky with light-based astronomy, something no gravitational wave detector can currently do, and determine how collisions between the most exotic and mysterious objects in the cosmos evolve over time. This is unlikely to be the end of the upgrades to gravitational wave detection alerts. At the end of this current operating run, LIGO/Virgo/KAGRA collaboration scientists will use data collected in nearly 2 years of listening to a universal symphony of colliding black holes and neutron stars to improve alert speed even further. And there you have it. Thank you for watching. If you enjoyed the video, don't forget to give it a thumbs up and leave a comment down below. Remember to subscribe to Luminary Cosmos for more insightful content like this. Until next time, stay curious and keep exploring.